Hello students and friends. So today we shall continue with the topic probability. So in the previous lecture we have gone through the first exercise 16.1 and all the related theory which was required to solve the problem of the first exercise, and here we shall begin with the second lecture wherein we start with defining what an event is and the occurrence of an event, types of events, etc. So let's begin. So let us consider an experiment where a coin is tossed twice. So what is the sample space? So I need to define the sample space when the coin is tossed twice. So I may get head and head again, head, tail, tail, head, and two tails. So this is the sample space, isn't it? Right. So now what is the outcome of me getting one head? So here I need to check. So I have two outcomes, HT and TH, where one head occurs. So here I have defined an event where one head occurs. So when I have to choose or find out the outcomes of one head occurring, definitely there will be a subset of the sample space. Okay, so therefore in general any event E is a subset of the sample space, right? So any event E, so you define any event, it's going to be a subset of sample space. So if I define an event, say A, which says that two head occurs, so then that would be HH. So A would be an event which is a subset of the sample space considered here. Or if I define an event where I get two tail occurring, so then this would be the subset of the sample space, that is TT, right? So let us consider a few events and let me write the subset. So the few events defined and the subset of the sample space S. So this is for the experiment where the coin is tossed twice. So when the coin is tossed twice, this happens to be the sample space, right? So by definition, so before we find out the subset for the given events, so by definition any subset E of the sample space S is called an event, right? So you define an event. What could be the event? The event is, say, getting exactly one head or getting one tail in the given experiment or getting two heads. So here any subset E of the given sample space is defined as an event. So let us consider a few events and let us write the subset which is the subset of the sample space. So what is the experiment? The experiment is tossing a coin twice. So this is going to be the sample space. So what are the events? Getting two tails. Okay, so let me define it as event A. So getting two tails is TT. So this definitely is a subset of the sample space S. Next, at least one tail. So at least one tail means I need to have one tail or more than one is also a possibility. So let me define this as event B. So at least one tail means I have HT, TH, and I can also have two tails, but I cannot have head because there is no occurrence of tail. At most one head. So what do you mean by at most? Maximum I could have one head or zero heads occurring. So this is an event C where I can have a case where there are no heads or one head. So that's the maximum. I cannot have two. So this is the event C, which is the subset of the sample space S. Next, at most two tails. So what do you mean by at most two tails? I can have zero tails occurring, one tail occurring, or two tails occurring. So let me define it as event D. So I have the entire sample space HH, HT, TH, and TT. So this is the sample space S itself. And then more than two tails. This is, let me call this as event E. So more than two tails. So can I have an outcome where there are more than two tails? No, because the coin is being tossed two times. So therefore maximum I could have two tails. So this is a null set. That means you do not have any outcome. So this defines the null. So the next concept is occurrence of an event. So what do we mean by occurrence of an event? So we define occurrence of an event as, now an event E of the sample space S is said to have occurred if an outcome W of an experiment is such that W belongs to E. If W does not belong to E, then we say that the event E has not occurred. So what do we mean by this? So let us consider an example of tossing a coin 3 times. So when a coin is tossed 3 times, we get one of these 8 combinations. That is 3 heads occurring, HHT, 1 head, tail head, and so on. So we get these 8 combinations. Now let me consider an event E where you have at least 1 head. So you have at least 1 head occurring. Right? So at least one head means that you can have 1 head, 2 or 3. So that means we consider these 7 combinations. Alright, now let me consider conducting an experiment of tossing a coin 3 times and I end up getting tail, 3 tails. Okay, so now the outcome of the experiment W does not belong to the event here. Now what is the event E? The event E is at least 1 head occurring. So you can have 1 head, 2 heads or 3 heads. So this is the event E, which is the subset of the entire sample space. But if I have an outcome W such that I get 3 tails, that means this outcome is not one of the outcomes present in the event E. So therefore we say that W does not belong to event E and E has not occurred. So let's take another example. If I consider a die being thrown, I get one of these combinations. I can get 1, 2, 3, 4, 5 or 6. So let me consider an event E where I have numbers between 1 and 3. So I have 1, 2 and 3. So event E is defined as getting the numbers less than 4. And suppose I toss the die, I get say a number 2. Say this is W1, which is 2. So W1 belongs to E. So we say that the event has occurred, right? So because the outcome W1 is present in the event E considered. But suppose I toss the die once again and I get W2 equal to 6. And we find that W2 does not belong to E. So we say that the event E has not occurred. So this is what we mean by saying occurrence of an event. Okay, so with this, let us move on and let us try to understand the types of events. So what are the types of events? The first category is impossible and sure events. So an impossible event is defined by an empty set phi, whereas a sure event is defined by the sample space S. Now what do we mean by phi? Phi means that it is an empty set, that is, it is an impossible event. For example, when I throw a die, me getting a number 7 or 8 is an impossible event. So this is the first type. The second one is a simple event. If an event E has only one sample point in the sample space S, it is referred to as a simple event or the elementary event. Now for example, if I consider tossing a coin 3 times, this is the sample space, and I define events E1 equal to HHH, E2 equal to HHT, and so on. Now we realize that all these events have only one sample point of the sample space, right? They only have one point. So therefore, such an event is referred to as a simple event, or it is also referred to as an elementary event. Now what is a compound event? If this is simple, now how do we define a compound event? Now a compound event is one where the event has more than one sample point. So suppose I have an event E3 having HHH, HTH, HTT and THH, for example. So this is an event having more than one sample point in the sample space, so therefore it is referred to as a compound event. Very simple. So what are the types of events? Impossible event and sure events. Sure events are sure to occur, whereas impossible events are such that a null set, you get a null set. For example, getting a 7 or an 8 when you throw a die, that corresponds to an impossible event. The next one is a simple event, where every event is represented by one sample point in the sample space. For example, here I have defined, or a compound event where you have more than one sample point in the sample space. So next we shall deal with the algebra of events. Now let us consider A, B, C be the events for the experiment with the sample space S. So A, B, C are the three events and S happens to be the sample space. Okay. The first one is a complementary event. It is defined as for every event A complementary, which is written by A dash, is also called as event not A. Right? So what is not A? For example, if I consider this to be the sample space, so I consider an experiment where a coin is tossed 3 times, so you get 8 combinations, and this happens to be the sample space. Now let me consider an event A wherein you have one tail occurring. So among heads and tails, only one tail occurs. So you have HHT, this is one combination, this is another combination HTH, and you get one more combination THH. So we have defined an event A where you only have one tail occurring in all its outcomes. Now what is A complement? A complement is all the outcomes which are not present in A but present in the sample space. So 3 of them are here. So what is A complement? It is definitely HHH. Then you have HTT. Then you have THT, TTH and TTT. So not of A is nothing but all the outcomes which are present in the sample space but not present in A. Next, second one, event A or B. So this actually indicates the union of the two sets A and B, or we define it as A union B, wherein you have an outcome W where W belongs to A or W belongs to B. All right. So you consider the union, that is combination. For example, if A is HHH and HTH, and if B is TTH and TTT. So what is A union B? A union B, or we can call it as A or B, is nothing but the combination of these two. That means you have HHH, HTH, TTH and TTT. Very simple. The next one, we have the event A and B. So this essentially means you have A intersection B. That means you have to write the outcomes which are common to both A and B. Now for example, if I consider A and B here, if I have to write A intersection B, which is defined as W, where W belongs to A and the outcome W belongs to B. So if I consider these two, what is A intersection B? Is there any outcome which is common to both A and B? No. So therefore it's going to be a null set. All right. So if there was something common, for example, if B had HTH, then A intersection B would be HTH, because HTH would be present here and as well as in event A. Fourth one, event A but not B. So this essentially means I have A minus B. I have to write A minus B, right? That means you have the outcome which is present in A but which is not in B. But not in B. So this is defined as A minus B, which is A intersection B dash, which indicates not of B here. So let's take an example. Now suppose I consider throwing a die. So therefore the sample space is 1, 2, 3, 4, 5 and 6. I consider event A, which is getting a prime number, right? So how do I define A? It is nothing but getting a prime number. So 2, 3, 5. So I have 2, 3, 5. And I have another event B, which defines me getting an odd number. So it is 1, 3 and 5. So let's take a few examples. What is A or B? A or B is A union B. That means I have to write what is present in A and B. So I have 1, 2, 3 and 5. So remember, the elements which are present in both A and B, you write it here. So you get 1, 2, 3 and 5. Second one, A and B, which is A intersection B. That means what is common between both A and B? What is common? 3 and 5 is common. So I write 3 and 5. Then third one, A but not in B. So this is A intersection B complement, which is nothing but A minus B. So what is there in A but is not there in B, right? So what is there in A which is not there in B? So I have 3, 5 which is there in B. But what is there in A which is not in B? I find that 2 is present in A but is not present in B. So it is nothing but 2. The next one, not of A. So not A is nothing but A complement. So I write all the outcomes which are not present in A, which is 1, 4 and 6. So with this basic introduction of algebra of events, so let's move on to what mutually exclusive events are and what are exhaustive events. So what are mutually exclusive events? Let us consider a die being thrown. So you get the sample space S as 1, 2, 3, 4, 5 and 6, isn't it? So now let me consider an event A wherein you get odd numbers. So I have 1, 3 and 5. And another event B, which includes even numbers. So me getting an even number when the die is thrown. So I have 2, 4, 6. Now I find that if I consider A intersection B, so A intersection B, so what is common between A and B? Nothing is common. It is a null set. So therefore A and B are said to be disjoint, or A and B define disjoint sets. Hence we conclude that A and B are mutually exclusive. So therefore A and B are mutually exclusive. So what is the definition? If the occurrence of one excludes the occurrence of another event, that means they cannot occur simultaneously. So A and B are said to be mutually exclusive if occurrence of any one excludes the occurrence of the other. That means both of them cannot occur simultaneously. So we have to note that simple events of a sample space are always mutually exclusive events. So what are simple events? I only have one of them, right? Let's assume that this is event A, B, C, D, E, F, G, H and so on. So we find that all these events are mutually exclusive because there is nothing common between the two. Next, we define exhaustive events. Now what is the definition? The definition is if events E1, E2 up to En are n events, they are nothing but n events of the sample space S, and if E1 union E2 union E3 or E1 or E2 or E3 and so on up to En, which is nothing but union of 1:n EI equals the sample space, then we say that E1 comma E2 and so on up to En are called exhaustive events. So let's again consider the sample space of a die being thrown. So you get 1, 2, 3, 4, 5 and 6. Now let me define an event A wherein you get numbers less than 4. So I have 1, 2 and 3. Event A is defined as one where you have numbers less than 4, and I have event B which is defined as the numbers greater than 2 and less than 5. So greater than 2 is 3, 4 and less than 5. So you just have 3 and 4. And an even C, which is defined as having numbers greater than 4, which is 5 and 6. So I find that if I take A or B or C, I get 1, 2, 3, 4, 5, 6. Right? So I have to combine all the outcomes of all these three events A, B and C. And what does this give me? This gives me the sample space S, which has been written here. So therefore A, B, C here are referred to as exhaustive events. So A, B, C are referred to as exhaustive events because if I consider A union B union C, I get the sample space. But if I consider only A union B, they are not exhaustive events because if I combine these two, I will only get 1, 2, 3, 4, and that is not equal to the sample space. So if I take the union of all the events considered, and if that gives me the sample space, then those events are referred to as exhaustive events. And this is what is required for us to solve the next exercise 16.2. So there are 7 easy problems. We shall solve all of them. So let's begin with the first one. So we are solving exercise 16.2, the first one. So you can see the problem on the screen. A die is rolled and I have event E, and event E is 4 and F represents an even number. An even number meaning what is F? It is 2, 4 and 6. Are E and F mutually exclusive? So what do you mean by mutually exclusive? It means that E and F have no term in common. But I find that E and F have one term in common, which is 4. So therefore, are they mutually exclusive? The answer is no. They are not mutually exclusive. That's the answer. The second one, a die is thrown. We need to describe the events. The first one, event A, where you get a number less than 7. So when a die is thrown, let me write the sample space. I get 1, 2, 3, 4, 5 or 6. So this is the sample space S when a die is thrown. And what is event A? The number is less than 7. So therefore A would be 1, 2, 3, 4, 5 and 6, and that is equal to S, the sample space. Second one, B, which is defined as the number greater than 7. So can I get any number greater than 7? No, it's not possible. So B is null. It's a null set. 3, even C is a multiple of 3. So since it is a multiple of 3, I have two numbers 3 and 6. So C equals 3, 6. So these two are multiples of 3. Next, what is D? Event D is defined as an event where you have numbers less than 4. What are the numbers less than 4? 1, 2 and 3. So I've defined event D. The fifth one, an event E, where you have an even number greater than 4. An even number greater than 4. So numbers greater than 4 are 5 and 6, and there is only one even number greater than 4, which is 6. So E is nothing but 6. Sixth one, event F, a number not less than 3. So I have to consider a number which is not less than 3. So I should not consider numbers which are not less than 3. So therefore the numbers which are less than 3 are 1 and 2. So leaving these two, I consider all of them. So F is 3, 4, 5 and 6. Right? So these are all the numbers which are not less than 3. Define the following. What is A union B? What is A union B? 1 to 6 and a null. So I have 1, 2, 3, 4, 5, 6. So write all the elements present in A. What are the elements present in B? There are no elements present in B. So I write the elements 1 to 6. Next one, A intersection B. Is there anything common between A and B? No. So you have 5, which is null. Then B union C. Now since this is null, when I combine B and C, I get 3 and 6. So this is going to be 3, 6. Very simple. Then E intersection F. So what is common between E and F? 6 is common. So I have 6 here. Next, D intersection E. What is common between D and E? Here I have 1, 2, 3. Here I have 6. There is nothing common. So therefore, it is null. Next one, A minus C. All the elements present in A which are not there in C. Now what is there in C? 3 and 6 is present in C. So all the elements which are present in A not there in C. So I have to eliminate 3 and 6 and write it here. So if I eliminate 3 and 6, I get 1, 2, 4 and 5. So 1, 2, 4 and 5. Next, D minus E. All the elements in D which are not there in E. It is nothing but 1, 2 and 3. Right? All the elements which are in D but not in E. So I find that there is nothing common, right? So all these 3 elements are not present in E, so I write 1, 2, 3 here. Next, E intersection F complement or F dash. What is E intersection F dash? Now we find that F is 3, 4, 5, 6. What is F dash? F dash would be, I'll write F dash here, all the elements present in the sample space but not present in F. So that is going to be 1 and 2. So find what is common between E and F dash. There is nothing common, so it is a null set 5. Right? So F dash is 1, 2. Right? So this was a pretty easy problem. The third one, we are rolling a pair of die. So when we roll a pair of die, what is the sample space? So the sample space would be, you may get 1, 1, then 1, 2, then 1, 3 or 1, 4, 1, 5 or 1, 6. Next I may get 2, 1, 2, 2 and so on up to 2, 6, and like this 3, 1 up to 3, 6. 4, 1 up to 4, 6, 5, 1 up to 5, 6, 6, 1 and 6, 6. So this is what I get on the first die, and the next one is what I get in the second die. So how many combinations are there? You have 6 into 6. So totally 36 outcomes or possibilities are there when I throw a pair of die. So what is event A? Event A is such that the sum is greater than 8. So when I take the sum, it should be greater than 8. Okay, let's see what they are. So in the first row, the maximum sum is 7. The second row, the maximum sum is 8. So it should be greater than 8. So that means it should be 9 onwards. So here I have 3, 5, which is 8. So in the third row, I have 3, 6, which is greater than 8. So I write 3, 6. Next, this is 4, 5, 4, 4. So greater than 8, I have to write these two. 4, 5, 4, 6. And then here, greater than 8. So I have 5, 2, 5, 3 is 8, 5, 4, 5, 5. So what is greater than 8? These 3 are greater than 8. So I have 5, 4, 5, 5 and 5, 6. And in the last row, greater than 8. So this is 6, 2, which is 8. So I have 6, 3, 2, 6, 6. All of them are greater than 8, isn't it? So you have 6, 3, 6, 4, 6, 5 and 6, 6. So they are all greater than 8. Next, even B. 2 occurs on either sides. So here you have to define the even B. So here you have to define an even B wherein 2 is occurring on either sides. So either 2 occurs here on the first die or on the second die. So what is the event? In the first row I have 1 comma 2. In the second row I have all the 6 combinations because 2 is occurring either on the first die or on the second. So I have 2 1, 2 2, 2 3, 2 4, 2 5 and 2 6. In the third row I have 3 2 where 2 occurs, so I write 3 2 here. In the fourth row I have 4 2. In the fifth row I have 5 2 and in the sixth I have 6 2. Alright, okay, so next C, sum, even C is defined as the sum which is at least 7 and a multiple of 3. At least 7 means the sum is 7 or greater than 7 and a multiple of 3. So I have to find the sum. I have to take the sum of two numbers and they have to be a multiple of 3, but it should be greater than 7. So greater than 7, what are the numbers which are multiples of 3? So I have 7 is not a multiple of 3, 8 is not a multiple of 3, I have 9 and then I have 12. So 9 and 12 are two numbers which are multiples of 3, which I would get when I add the two numbers because the highest number is 6 6, isn't it? Right. So now how do I define? So I have to check all the combinations which when added gives me 9. So here till here I will not get 9 because 6 plus 2 is 8. So here I have 3 comma 6. So 3 plus 6 is 9 and is a multiple of 3. Next, the fourth row I have 4 comma 5 is 9 and a multiple of 3. Next, the fifth row I have 5 comma 4 is 9 and a multiple of 3. Right? Next, here I have 6 comma 3 is 9, a multiple of 3, and 6 comma 6 is 12 and a multiple of 3. So I have 5 outcomes: 3 6, 6 3, 4 5, 5 4 and 6 6. So these are the outcomes of the event C. Now I need to check if event A and B are mutually exclusive. So if I check A and B, I find that none of the events or none of the outcomes are common between A and B, isn't it? So there is nothing common between A and B. So A and B are mutually exclusive. They are mutually exclusive. And what about B and C? B and C are also mutually exclusive. If you observe B and C, there is nothing common. B and C are also mutually exclusive. But what about A and C? A and C is not mutually exclusive because I find that 3 6 is present in both the places, 4 5 is present in both the places. So even if one of the outcome is present in both the places, they are not mutually exclusive. So AB is mutually exclusive, B and C is mutually exclusive. So problem 4, 3 coins are tossed. So if 3 coins are tossed, this is the sample space. I've just written it here. You get head, 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 2 heads and a tail, and so on up to 3 tails. So you have 8 combinations. So event A is defined where we get 3 heads. So it is the first one. So A is nothing but head, head, head. And what is event B? Event B is where you get 2 heads and 1 tail. So event B is 2 heads and 1 tail. So this is 2 heads, 1 tail, 2 heads, 1 tail, and this one. So I get H, H, T, H, T, H, and T, H, H. 2 heads and 1 tail. Event C is defined as getting 3 tails. So this is the outcome, T, T, T. And event D is defined as the outcome where the first is a head. So I have these 4 combinations, right? These 4 outcomes. So H, 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 T, H, T, H, and H, T, T. And for all the other 4, we get tail in the first place. So these 4 combinations form event D here. Problem 1. Which of them are mutually exclusive? Let me consider A and B. Is there anything common between A and B? No. So A and B are definitely mutually exclusive. Next, is there anything common between A and C? No. So therefore A and C is mutually exclusive. Is there anything common between A and D? Yes. Head. 3 heads are common. So A and D is not mutually exclusive. Now let us consider B and C. Is there anything common between B and C? No. B and C are mutually exclusive. And what about B and D? Is there anything common? Yes. 2 heads and a tail, 2 heads and a tail. So B and D is not mutually exclusive. And then now let me consider C and D. Is there anything common between C and D? No. So C and D are mutually exclusive. So we have 4 events. That's 4 combinations, that is A and B, A and C, B and C, and C and D are mutually exclusive. 2. Which of them are simple events? Now we consider an event to be simple if you have only one outcome. So that is event A and event C. So A and C are simple events. So event A is a simple event, event C is also a simple event. Third one, compound. Definitely B and D are compound events. Why is it compound? Because you have more than one outcomes occurring. Fifth one, 3 coins are tossed. Describe 2 events which are mutually exclusive. Now I need to define 2 events which are mutually exclusive. So definitely here itself we have an example. So 3 heads and 3 tails, they are mutually exclusive. You can have different answers. So you just have to give one example. 3 heads and 3 tails, they are mutually exclusive. Getting at least 2 heads and 2 tails are again mutually exclusive. So this is one answer. So at least 2 heads and at least 2 tails is again mutually exclusive. Second one, 3 events which are mutually exclusive and exhaustive. So let us consider a case where we have no heads, an event. So that is 3 tails. And let us consider an event where there is 1 head. So when we consider 1 head, I have head, tail, 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 head, tail, 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 head. So I have these 3 combinations. And I consider one more where there is at least 2 heads. So at least 2 heads means you have 2 heads and you can have more than that. So let me just stick them there itself. So instead of writing no heads is this combination. At least 1 head. So I have head, tail, tail. So this is tail, head, tail. And then you have 2 tails and a head. At least 2 heads. So here you have 2 heads, 2 heads, 2 heads and 3 heads. At least 2 means you can have 2 and more than 2. So you have this combination, this, this and this. Alright. So now if I take the union of all these 3 events, what do I get? I get the sample space because I've covered all the 8. So this is an example where I have 3 events which are mutually exclusive. So remember, they are mutually exclusive. There is nothing common, but they are exhaustive also, because if I take the union of all the 3, what happens? I get the sample space. So this is an example. Third one, 2 events and they are not mutually exclusive. So I need to consider 2 events, but they are not mutually exclusive. So let us consider an event where you have 1 head and then I have at most 1 head. What do you mean by one head? I have these three combinations: head, tail, 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 head, tail, 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 head. And what do you mean by at most one head? You can have no heads, three tails, and at most one means maximum of one head. So you get head, tail, 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 head, tail, 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 head. So here I have two events, but they are not mutually exclusive because I find that these three are common between the two. So these are two events which are not mutually exclusive. Next, fourth one, two events which are mutually exclusive but not exhaustive. So they are mutually exclusive but not exhaustive. So they are not, it is not exhaustive. So what are two events which are mutually exclusive? Let me consider these two combinations: three heads and three tails. Three tails and three heads. Two events. Are they mutually exclusive? Yes. But are they exhaustive? No, because if I take the union of these two, I do not get the sample space. So this is one example. So you can have a number of examples. Okay, so there's no hard and fast rule that you have to write these answers. You can have different answers too, and they will be right too. And the last one, three events which are mutually exclusive but not exhaustive. Okay, now let me consider the three events as having three tails, having two tails, and having exactly one tail. Right? So let me mark the outcomes here itself, and let us see if they are mutually exclusive. Three tails, exactly three tails is this combination with a tick mark. Exactly two tails. So I have this combination, this combination, this combination, and then exactly one tail. So I indicate by circle one tail, one tail, one tail. Is there anything common between the circle, the arrow, and a tick mark? No. That means these three are mutually exclusive. These three events are mutually exclusive, but are they exhaustive? No, because there is one outcome which has been left out. If I combine all these three events, I still do not get the sample space. So this is an example of three events which are mutually exclusive, but they are not exhaustive. So let's move on to problem 6. Problem 6, two dice are thrown and I have events A, B and C. Event A is defined as one where you have an even number on the first die. So you have even number on first die. Event B is defined as you have an odd number on the first die. And event C is defined as one where the sum of numbers on the die is less than or equal to 5. So what is event A? I have even number on the first die. So I have the second row, the fourth row and the sixth row, isn't it? So you have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Next you have 4, 1, 4, 2, 4, 3. So this is event A, where the first number is even. So you have 2, 1 to 2, 6, 4, 1 to 4, 6, 6, 1 to 6, 6. And then I have event B, where the first number is an odd number. The number on the first die. So I have 1, 1, 2, 1, 6. So I'll not write all of them. You can write it. 3, 1, 2, 3, 6. So that is the first row, the third row and the fifth row. 5, 1, 2, 5, 6. Right? So 18 combinations here, 18 combinations here. And remember that they are not overlapping. Right? So A and B are mutually exclusive. Right? First one. What is not of A? Not of A is all that which is present in the sample space but not in A. It is nothing but the numbers having an odd number on the first die. So it is nothing but B. What about the second one? Not B. Not B is nothing but B dash, which is A. Not of B is what is not present in B but is present in the sample space, which is nothing but A. Third one, A or B is nothing but A union B, which is the entire sample space. Fourth one, A and B, which is A intersection B, which is a null set 5. I've already told you that there is nothing common between A and B. They are mutually exclusive. So therefore, A intersection B is null. Fifth one, A but not C. So we have not defined C. What is C? So C is the outcome where the sum of numbers on the die is less than or equal to 4. So what is C? It should be less than or equal to 5. That means from 2 to 5, right? So I check. So here 1 plus 1 is 2. So I have the first one, 1, 2, 1, 3 and 1, 4. So up to 5, less than or equal to 5. So I have 1, 1 to 1, 4. In the second row, I would have 2, 1, 2, 2 and 2, 3 up to 5. Next, in the third row, I have 3, 1, 3, 2. So this is 5. 3, 3 would be 6. So it is not included. Next one, 4, 1 is 5. What about the element in the fifth row? 5, 1. 5 plus 1 is 6. So none of the elements in either row 5 or row 6 will be an outcome in even C. So I have these. So the fifth one states that A but not in C. That means A minus C. All of them which are there in A but not in C. So what is present in C? Of course, nothing starting with 1 is present in C. 2, 1, 2, 2, 2, 3 is present in C. Okay. So what is not present in C but present in A? You have 2, 4, 2, 5 and 2, 6. Next, 4, 1 is present. So that gets scored out. The remaining 4, 2 to 4, 6. And then of course 6, 1 to 6, 6. So all the elements which are present in A but not present in C. So I get 2, 4, 2, 5, 2, 6, 4, 2 to 4, 6, all of them. And then 6, 1 to 6, 6. Next I have B or C. That means it is nothing but B union C. So B refers to all the outcomes where the first number is odd. So I have 1, 1, 2, 1, 6. Then let me consider even C here. So I have 2, 1, 2, 2, 2, 3, right? And then of course I have 3, 1 all the way up to 3, 6. And then I have 4, 1 which is present only in C. And then 5, 1 up to 5, 6. Alright, so this is B union C. Now seventh one, B and C. What is B and C? It is B intersection C. So what is common between B and C? I have 1, 1, 1, 2, 1, 3, 1, 4 which is common between these two. So I write them 1, 1, 1, 2, 1, 3 and 1, 4. Of course, anything starting with 2 is not present in B. Next, I have 3, 1 and 3, 2. So 3, 1 and 3, 2. Next, do you have anything starting with 4 in B? No, and nothing in 5. So these are the combinations 1, 1, 1, 2, 1, 3, 1, 4, 3, 1 and 3, 2. The last one, A intersection B dash intersection C dash. So A intersection B dash. What is B dash? B dash is nothing but A, right? So I can write this as A intersection C dash. What is A intersection A? All the elements which are present in A itself. So I have A intersection C dash. Alright, so now I have to write the elements which are common between A and C dash. What is C dash? All the elements in the sample space which are not there in C. Okay, so now I need to check all the elements which are not there in C, which are in common with A. What are the elements not there in C? The elements which are not there in C is, so let me write C dash. I have 1, 5, 1, 6. Then I have 2, 4 to 2, 6. Then I have 3, 3 to 3, 6. Then I have 4, 2 to 4, 6. 5, 1 to 5, 6. 6, 1 to 6, 6. So these are all the elements in C dash, right? The elements in the sample space which are not there in C. Now, what is common between A and C dash? Just check, observe. So you have 1, 5, 1, 6 is not common, right? Then you have 2, 4, 2, 5, 2, 6, which is common. So therefore, A intersection C dash is 2, 4, 2, 5, 2, 6. Then is anything present starting with 3? No. What about 4? Yes, 4, 2 to 4, 6. So I'll write this as 4, 2 to 4, 6. Is anything present starting with 5 and A? No. Then what about 6? Yes, 6, 1 to 6, 6. So 6, 1 up to 6, 6. So in the test or in the examination, you have to write all the outcomes. Just don't put dash dash. Okay, so make sure that you write all the outcomes in the test or in the examination. Next, seventh one. So we have to refer the sixth problem and we have to answer. First one, A and B are mutually exclusive. Yes, they are mutually exclusive. It is a true statement because there is nothing common between A and B. 2. A and B are mutually exclusive and are exhaustive. Is it true? Yes, because A and B are not only mutually exclusive, but if I combine A and B, I get the entire sample space, so it is a true statement. 3. A equals B dash. Now what is not of B? Not of B is all the elements in the sample space which are not there in B. So that means that B dash is the rows 2, 4 and 6, which is nothing but event A. So A equals B dash is a true statement. Fourth one, A and C are mutually exclusive. Is A and C mutually exclusive? Just check if there are any common outcomes. You find that 2, 1 and 2, 1 is common, 2, 2, 2, 2 is common. So therefore, it is a false statement. Next, fifth one, A and B dash are mutually exclusive. Now, B dash is nothing but A itself. We have just seen that. How can A and A be mutually exclusive? Because you would have the elements which are common, right? A and A dash are one and A and B dash are one and the same. So A and B dash meaning A and A itself. They cannot be mutually exclusive because we are referring to the two events which are the same. So this again is a false statement. Next, sixth one, A dash, B dash and C are mutually exclusive and exhaustive. A dash, B dash and C. So if I consider A dash, B dash and C, what is A dash? It is B. What is B dash? Is A. And I have C. Are they mutually exclusive? No. A, B are mutually exclusive, but not A, B and C. They are not mutually exclusive and exhaustive. It may be exhaustive if I consider A, B and C it is exhaustive, but they are not mutually exclusive. So both the conditions have to be satisfied. Since A, B and C are not mutually exclusive, one of the condition fails, so therefore this statement is a false statement. So for this to be a true statement, both the conditions have to be true. They have to be both mutually exclusive and exhaustive. They are not mutually exclusive, but they are exhaustive. One of the condition is not true, so we say that this statement is false. So in this video, we have gone through the fundamentals of events. We have seen what are the different types of events, algebra of events, and we have also discussed what is, and we have also discussed what mutually exclusive events are and what exhaustive events are. And we have also solved all the problems given in the second exercise, that is 16.2. In the next video, we shall deal with probability and solve all the problems given in the third exercise, which is 16.3. And let me tell you, all the problems are very easy. Okay, so make sure that you keep solving more and more problems so that you find this topic pretty easy. So this topic, probability, is definitely one of the easiest topics in class 11th. So keep solving problems. Do not forget to view all the other videos in class 11 mathematics, and do not forget to like, share and subscribe, and press the bell icon to get notifications of all the further uploads. And thanks for watching.